Okay, so this is a basic primer, an introductory, very simple revision lecture on what are the basics of matrices. First, let's start where we should be starting, which is what is a matrix, in fact. In the mathematics that you've studied up to this point, mostly, we've been looking at the variable x, for instance, or the independent variable x and the dependent variable y. And at the end of the day, the variable x or y, whatever it is, has at the end one numerical value that you are searching for sometimes. So that one value is sufficient to describe the variable. Okay. So for instance, if x equals 2, that means that's it. X equals this one numerical value 2, and that's it. You do not need a second value to describe x. Now, I don't mean that x cannot take more than one value. X, in terms of roots, for instance, a quadratic, the x has two possibilities. For a cubic, it has 3, and so on. That's not what I'm talking about. Or in case of a sine or cosine function, it has an infinite number of possible roots. What I mean here is that an equation in x has a solution, and if then that solution, one value suffices to describe or explain. For instance, the height of a person. Okay. Height of a person, only one number, like for instance, I don't know, 62 inches. Okay. So you need 62 inches. You don't need a second number. A person cannot be 62 inches and 56 inches at the same time. That's not possible. So height requires this. Okay, the time at a certain point, the weight of a person, and so on. These variables or these entities require only one number to describe them. What about the case where one entity is described by several numbers? If I give you for instance here, on the xy domain, here's a point. Now this point has an x coordinate. Let's call it x1, and a y coordinate. Let's call it y1. Now, is it sufficient to say, is one number sufficient to describe it? No. Okay. If you want this point in location, you need x1 and y1. Once you know that, you know this in this direction, I'll move these many points, or this far, and in this direction I'll move this far, and I'll get this point. So our two numbers are required to describe this particular point. But anyway, here what I'm trying to say is that there are situations where we need more than one point. In 3 dimensions, instead of x1, y1, you would have x1, y1, z1, for instance. So you could have x1, y1, and z1. So 3 numbers are required to describe it. If you add time, there could be 4 numbers are required to describe it, and so on and so forth. So therefore, there are many possibilities in where one number is represented, one variable has many numbers representing it. This is precisely where the concept of a matrix enters. A matrix is a mechanism whereby many numbers can be stored to represent one variable. Okay, that's the easiest way to think about it. Mostly you would be familiar, since this is a revision, you would be familiar that a matrix usually has either large square brackets, or maybe sometimes the circular brackets. And inside these large brackets, you have numbers like these numbers. Okay. So, and usually a matrix has a letter, for instance, a capital letter A is this matrix, described by 9 numbers that you see here. So this matrix is described by 9 numbers. It requires 9 numbers to describe it. Whatever it is, that's not important right now. We will see examples of this as we progress through the linear algebra course. Some very few important properties of matrices. And these are, number 1, the size of a matrix. So let's talk about size. Okay? Size of a matrix. Size of a matrix is always described in this manner: row by column. Row by column. Okay? Row by column. So number of rows by number of columns. So for instance, the matrix you see here, okay, this has got 1, 2, 3 columns, and it's got 1, 2, 3 rows. So this will be a 3 by 3 matrix. Okay, let's look at another example. Here's another matrix, and let's make it a different type of matrix so that so that you can see them as different. Now this has got 2 rows, so we'll do the number of rows first. So 2 by, it's got 1, 2, 3 columns. So it's a 2 by 3 matrix. So this one is a 2 by 3 matrix. This one is a 3 by 3 matrix. So I hope you get the idea. The next thing we need is this to identify the location of one of the numbers. For instance, if I wanted this particular number, where is this number in the matrix? How do I get access to it? How do I do any algebra related to this number? Okay, if I want to pull this number out of this matrix, how would I do that? For that, we have we introduced the concept of indices and general matrices, and that's what I'm going to do next. So I'm going to introduce the sort of this symbology that we use for representing general matrices. So what I'm talking about is, for instance, let's look at a particular number. Let's say this is A, for the sake of argument. Where is this number located? Well, it's in row 1. So row 1 and column 1. So I can, that means the elements in a matrix can be written like this: row and C, row and column, row and column. So for instance, the second number here, A, let's say it's A because it's a general matrix. What row is this? Still row 1. And what column is this? It's the second column. This is the first column. This is the second column. So let's go to the third one then. A, 1, 3. And you get the idea. First column, the first row is row 1. And this goes on, let's say, till for n columns. So it's on till n columns. Now let's look at the second row. Second row would be 2, 1, 2, 2, 2, 3, and 2n. And similarly, as we go down, this will go up to, let's be flexible. We're not looking at a square matrix, so we're not looking at n by n. Let's make it m. M rows, first column. Mth row, second column. Mth row, third column. And mth row, nth column. So there, now you can clearly see a very simple, straightforward way of representing a general matrix. So we learn 2 things from this. We can access any number in the matrix by simply knowing its address. So you should think of these numbers, these indices, as the address of the number in the matrix. So it's the, you can address, okay? Okay, so this is the address, this here. This is the address. You can think of it this way. So I'm going to put it in quotes. This is not necessarily what you'll find in your book, I'm not sure, but or where you read it, but you can think of it as the address of the number. And since you're computer science students, addresses are quite important, memory locations or what have you. Or in the one very quick application of matrices that you should be familiar with are, for instance, arrays. But anyway, we'll come to these things later on. So this is the address of any particular number in the matrix. Okay, so that is some basic notation of how we can represent general matrices. Next, let's get to the next important point, which is matrix algebra. So I want to look at matrix algebra. What do I mean by matrix algebra? Well, it's a large topic, but at the moment, I'm only going to look at, for instance, addition and subtraction. Okay, let's look at these 2 first because both are similar always. Okay. One is taking away, one is adding on. So let's have a look. How does matrix addition work? There are rules. There are very important rules for matrix algebra. For addition, the major rule, unbreakable rule is both matrices, the matrices being added must be of the same size. Added or subtracted. Okay, so both matrices have to be exactly the same size for addition to be possible. So, for instance, let me give you a quick example. So you have 1, 2, 3, 4. This matrix and this matrix here, let's call this A, and let's call this one B. So this is 5, 7, 9, 1. Can these two matrices be added? Yes. What's the size of this matrix? It's 2 by 2. What's the size of this matrix? 2 by 2. So addition is possible. How do we add? Let's have a look. Basic addition is done by adding the corresponding elements. So this element here is added to this element here. Okay? So the total becomes, so it's 1 plus 5. So it's 1 plus 5. And then 2 plus 7. Okay? Then 3 plus 9. The corresponding element in the two matrices, 4 plus 1. Okay, so it's equal to 6, 9, 12, 5. So that's the sum of the matrix. In the same way, you can subtract the two as well. Okay, so if I wanted to subtract these, then all it would be is this. I would be subtracting these, and so A minus B. So A plus B is this one. A minus B would be 1 minus 5 is minus 4. 2 minus 7 is minus 5. 3 minus 9 is minus 6. 4 minus 1 is 3. So you can see that addition and subtraction, very similar to each other. The addition rules, we add numbers the same way and subtract numbers the same way. The only thing is that the most important thing, matrices must be of the same size and corresponding elements are added or subtracted from each other as required. So that's addition and subtraction. Let's move on to multiplication. So, multiplication. Rule. Okay, number of columns of the first matrix order is very important. A times B is not necessarily the same as B times A. So you have to be careful with that. Whereas in addition and subtraction, A plus B is the same as B plus A, right? It doesn't apply to A minus B. Remember, there'll be a sign change because it's subtraction. But anyway, number of columns of the first matrix, okay, must be equal to the number of rows of the second matrix. Okay, so the number of columns of the first matrix must equal the number of rows of the second matrix. So let's have a look at this. So we are talking about, as an example, let's say I'm going to leave it open for a minute. And what I'm going to do is I'm only going to define the number of columns and I'm just going to look at the first row. So 2, 3, 5. So let's say the matrix is, we'll leave it blank for a minute, how many rows it has. Let's look at the second matrix. Let's call this A. And let's look at the second matrix. And let the second matrix. Now, if multiplication is going to be possible, this has to be 1, 0, 3. There have to be 3 elements here. So the number of columns of the first one, So the number of columns of the first one, 1, 2, 3 columns, must equal the number of rows, 1, 2, 3. So these two, the number of columns of the first, number of rows of the second, they must be equal. That's what this rule says. Okay? Then addition or multiplication is possible. So that's the rule. Now let's just, it can have as many rows. Okay? So the number of rows of this one, number of rows, you can have 50 billion rows here or just one row, doesn't matter. It's irrelevant. It will not stop the multiplication. It is relevant, but it will not cause any problems with the multiplication process itself, okay, or the mechanism of multiplying two matrices. In the same way, this matrix can have like umpteen columns here, okay, and it doesn't matter how many columns it has. So what I'm going to do is I'm going to do only, for instance, here, just two rows in the first one, and let's say 2 columns in the second one. Now I'm going to show you how we actually multiply. So let's see how multiplication works. What we do is we take the first element here, okay, and multiply it by the first element here. That's easy enough. So it's 2 times 1. I'm going to show you that exactly. Then we add the second element, which is this one, multiplied by this one. Okay, so that will be 3 multiplied by 0, and I'm going to write it down. I know it's 0, but just to demonstrate. And the last one, 5 and 3. Okay, so 5 times 3. Yeah, you might be thinking, why did I color the first two red and the last one blue? Yeah, whatever. Anyway, so 2 times 1 plus 3 times 0 plus 5 times 3. So we've got, and then we just do that sum, and that's the first element in the product matrix. Okay, or in other words, in AB. I shouldn't say, sorry, here. AB equals, sorry about that. Okay, AB equals, this is AB I'm calculating. Now, what will I do next? 2 times 4 is 8, plus 3 times 4 is 12, plus 5 times 4 is 20. Okay, so as we progress, I'm just going to make it clear what we're doing, hopefully. 1 times 1 is 1, plus 2 times 0 is 0, plus 1 times 3 is 3. And the last one is 1 times 4 is 4, plus 2 times 4 is 8, plus 1 times 4 is 4. Okay. So therefore, AB is equal to final 2 plus 5 threes is 15, so it's equal to 17. 8 plus 12 is 20, and 20 is 40. 1 plus 3 is 4, and here 4 and 4, 8 and 8, 16. So this is our resulting matrix, AB. Now, one important thing I'll tell you is that generally, if A is a matrix of size as, let's say, m by n, so A is an m by n matrix, and B, okay, B is an n by, let's say B is n by s, the number of columns of this one is n, and the number of rows of this one is n. So they are equal. So therefore multiplication is possible. So the resulting matrix AB, okay, AB, the size of this matrix will be m by s. So what it does is it takes the number of rows of the first matrix and the number of columns of the second matrix. And that's what results. So that's another very useful thing for you to keep in mind. You can check your answer. If we look at the case we were looking at, this example here, as you can see, this matrix here is a 2 by 3 matrix. This one here is a 3 by 2 matrix. And the result is, the result matrix here, this one, okay, is a 2 by 2 matrix. Okay, so that's multiplication in a nutshell, very quickly showing you how to multiply and the important rule for multiplication, which is if violated is not possible. You cannot multiply if the number of columns of the first one does not equal to the number of rows of the second. Okay. Now, when it comes to division, division is the most complicated of all the operations, of all the algebraic operations for matrices. We don't call it division. In fact, we call it the inverse of a matrix. The inverse of a matrix is a complicated idea. It is because we're not looking at, in this course in linear algebra, we're not going to be looking at the ability to do 2 by 2 matrices or 3 by 3 matrices or small matrices. We're going to have to look at, we want to be able to look at very large matrices. Now, one of the rules, there are several rules in division, but I will try to cover these a bit later on, because in order to be able to do the inverse of a matrix, we also need to understand another concept called the determinant of a matrix. Okay, so these are not introductory or not necessarily considered basic as far as I'm concerned. The basic thing I wanted to revise with you was simply addition and multiplication. The inverse of a matrix, you may know the inverse of a 2 by 2 matrix, but I will cover the inverse as a full topic in this course a bit later on, once the time is right. But I will tell you this, that division of a matrix is not done, for instance, of 2 matrices, A and B is not done A over B. Also, inverse, very basically, I'll tell you, and I'll revise this later, inverses of 2 matrices, the matrices have to be square matrices. Okay, this is another property of matrices which we will cover later. They have to be square, which means they are n by n only. So n by n only, matrices that are n by n, we can compute their inverse. We cannot compute the inverse of every matrix. Okay, so it's only possible to calculate the inverse of an n by n matrix, which are called square matrices. But not to worry, we will cover all these special properties of matrices a bit later on in the course. For now, this is sufficient for you to grasp some basic ideas of matrices, this is all revision, considered revision. Everything else we will cover later. Thank you.